examples go along with section 1.4. What we're going to be doing is finding the missing values. Sometimes we'll find 1, sometimes we'll find 2. And our purpose in finding the missing values is to make a function, usually a piecewise function, continuous. We're going to take a look at this piecewise function, and we want to make it into a continuous function by selecting the correct number. All right?
Any student that was a teacher or coach must report to the library now.
Now you know exactly what time I was making these notes. All right, so I have this piecewise function, and to one side, to the left side, the bottom function is in control, and to the right side of -1, the top function is in control. But it's missing something. It's missing this value right here. So we want to use the definition of continuity to create a continuous function. So we're going to start with knowing that in order for this to be continuous, as I approach -1 from the left, I have to get the same answer when I approach -1 from the right. That way, they're coming at the same thing. And the final piece of the puzzle is you have to actually get there. So we don't want a gap, but neither do we want a hole in the function. We want everything to come together and be continuous. Okay, so this step right here is a calculus step that you put in. If you leave this step out, you may not get full credit for your analysis if they're looking for you to show specific limit notation. Okay, this piece right here says go from the left, and the left side is the bottom function, so I'm going to plug -1 in for the x, -1 minus 3. This piece is from the right-hand side, so I'm going to plug in -1 for x. Notice I don't plug it in for a, I plug it in for x. And this final piece over here is also from the top function, because that's where the equals is. So it looks exactly the same as the center piece. And as soon as you recognize that this piece is the same as either one of these, then you can just leave it out. You should definitely write it in here. And it's not a bad idea to write it right here as well, but then after this point you can leave it out. Okay, now I'm going to solve this equation and see what happens. This side gives me -4, this gives me -a plus 2, and I'm going to solve that for a, subtract 2 from both sides, and divide both sides by -1, and I get that a equals 6. The directions were to find a, and what we have done is create a piecewise function that will be continuous. These two pieces of the puzzle will fit together at -1. There will not be a hole, and there will not be a gap. All right? The second one is a little bit more complex because there are 2 missing values in the second one. And there are 3 pieces to the piecewise puzzle. So before -2, this piece is in control. Between -2 and 3 inclusive, this piece is in control. And after +3, this piece is in control. And this time I have 2 missing values, A and B. So in order to make this one continuous, there are 2 places where it switches, and we're going to have to check out both places. So we're going to check out what's going on at x equals -2. The limit as x approaches -2 from the left has to equal the limit as x approaches -2 from the right, has to equal f of -2. -2 from the left is the top function, that's this, that's just 3. -2 from the right is the middle function, so I'm going to say a times -2 plus b. And at -2, the value of the function is also the middle function. So again, once I've written that down, I don't really need to keep up with it because it's the same thing as this middle one. So I have one equation here, 3 equals -2a plus b. There's my first piece of information. Now I'm going to do exactly the same thing at 3. I think probably you have enough room to do this over here at the side. I don't think I can write solid up or fit there, so let's put it underneath. So I'm going to check out what's going on at x equals 3. The same situation, the limit as x approaches 3 from the left has got to equal the limit as x approaches 3 from the right, and that has to equal f of 3. So to the left of 3, the middle piece is in control, so you'll say a times 3 plus b. To the right of 3, the bottom piece is in control, negative 3, and equals 3, the middle piece again. And once again, I can leave that off after I've noted that it's there. And I now get this equation, 3a plus b equals negative 3. There's no second piece of information. Now, I'm not done yet. I have to find out what a and b are. So I'm going to pull those two pieces together. The first one that I got was 2a plus b equals 3. I'm just going to make sure I got that right. Oh, also I have a discrepancy in my notes. I rearranged it. 2. We're going to just pause here for a second while I make sure I have this right. Negative, there it is, negative 2a, sorry, plus b equals 3. And the second equation, 3a plus b equals negative 3. This is a system of equations. You need to solve it. There are various methods. You can add them together. You can do substitution. There's multiple ways to do this. I'm going to just add them. It looks like if I add them, I'm going to subtract them. It looks like if I subtract them, the b's will go away. So I think you'll all remember doing that. Negative 2 minus 3, negative 5a, the b's disappear, and 3 minus negative 3 is 6. And the value of a, what's going to make this work, is negative 6/5. An unexpected value, but a correct one. And then after you get the first value, you've got to find b. You can pick either one, either this one or this one, whichever one feels easier to you. I'll pick the bottom, and I don't think it really makes a whole lot of difference. And plug in your a value into there. And solve for b. And so you've got to do a little bit of arithmetic. You are certainly expected to be able to do this level of arithmetic without your calculator. You won't have to do a lot of it, but you'll have to do it often enough that you ought to be able to handle it. Negative 3 plus 18 over 5. Get yourself a common denominator. If you don't practice it, sorry, that's supposed to be 5. If you don't practice it, you're never going to get good at it. And I get that b equals 3/5. So the solution, I was asked to find a and b, and the answer is a is negative 6/5, and b is positive 3/5. And if I wrote the function, that function would look like this. And that function would be continuous, right? I have one more to work through. And that's this weird kind of piecewise function where one function is controlled everywhere except at one place. We saw one of these earlier in class. So this top function is in control for every number except the number negative 5. And the bottom number is in control when the number is negative 5. All right? So the only interesting place here is negative 5. The limit as x approaches negative 5 from the left equals the limit as x approaches negative 5 from the right has to equal f of negative 5. So in this case, the limit from the left and the right are both controlled by the top function. So every single number goes into the top function up here, into this one, except the number 5. So these two things are the same thing. And I am plugging in the number, in order to do that, I have to plug in the number 5. You'll notice that if you plug in 5, you're going to get 0 over 0, so you have to write a separate limit statement for this. The limit as x approaches 5, left or right, of f of x is going to be minus the dual of factor and reduce. I'm going to plug it into this function, and that has to equal f of negative 5. Okay, so here it is. The limit from the left equals the limit from the right. Therefore, it's just the limit of x as x approaches just plain 5. You don't have to do two separate ones. And now I can plug in the negative 5. I've lost my negative along right here. It's right there. And I'm going to plug in my negative 5 minus 5. And this is value A from your function here. All right, and that tells me that negative 10 has to equal A. So if I want this function to be continuous, this number has to be negative 10. Okay. All right, so 3 different examples of continuity. And I had one little sort of pulling together some information just to make sure that you have all of this in one place. If you get the limit as x approaches c from the left is equal to the limit as x approaches c from the right, and both of those values are equal f of c, then you can tell me that it is continuous at x equals c. You have to have all of that information in order to justify continuity. If you get that the limit as x approaches c from the left is equal to the limit as x approaches c from the right, then the limit exists. But if it does not equal f of c, what we have here is that the limit as x approaches c exists, but it does not equal the value of the function. Then what you have is a hole. Okay? If f of c actually exists, then you have a hole with the crazy point. If f of c does not exist, then you just have a hole with no crazy point. And the third one, the limit as x approaches c from the left. If it does not equal the limit as x approaches c from the right, what did I see? C from the left. If those two are not equal, but if they both exist, now they have to both have an answer here. They can't have to equal some number. So that's equal k. Then what you have is a gap or a break. This tends to happen in piecewise functions. And in the last one, which we're going to look at a little bit more in the next class, is if the limit as x approaches c from the right does not exist, heading off towards infinity or negative infinity. And if the limit as x approaches c from the right, same thing, does not exist. Again, if this is approaching infinity or negative infinity, then what you're going to get is a vertical asymptote. Okay, and we're going to talk more about vertical asymptotes and these particular types of limits right here in section 3.5. All right, thank you very much.